Hi guys, I welcome you all for the course Manipulator Robotics Theory course. Today we are going to see dynamics for RP manipulator. Already we have discussed dynamics for RR manipulator. So the dynamics we are going to use is to derive the dynamics, the logic we are going to use is Lagrangian Euler formulation. So just a recap on Lagrangian Euler formulation. So what is Lagrangian? Lagrangian is equal to kinetic energy minus potential energy. And then tau y is equivalent to d by dt of dou L by dou QA dot minus dou L minus dou Qi. Okay. So here this is RP manipulator. So first your tau 1. First talk is d by dt of dou L by dou theta 1 dot minus dou L by dou theta 1. Okay. And tau 2 is d by dt of dou L by dou d2 dot minus dou L by dou d2. Okay. So we are going to derive this. So let's take this manipulator. So here, so this is my RP manipulator. Okay, so this rotates like this and it moves like this. So this is revolute and then this is static. Okay, so the length is L or let's say R for a change. Okay, R, and then the angle it makes is theta. Okay, so this is here we have end effector. This position is xy. Okay, so let's derive this. So first we have to derive kinetic energy. Kinetic energy 1 is equal to half m1 v1 square. So what is v1 square? V1 square is equal to x1 dot square plus y1 dot square. So what is x1? We know that x1 is here r cos theta. Okay, r cos theta. And then x1 dot is r cos already we have discussed in that. Okay, so this is r, this is theta, so this is r cos theta. So this is here x1. So if you take the derivative, it becomes minus r sine theta and then dot. And then y1 equal to r sine theta and y1 dot is r cos theta. And these are all or let's have theta 1 is not an issue because the other term is d only. So r cos theta dot. Okay. So your x1 dot square plus y1 dot square is equivalent to when you combine this, you will have r square theta dot square. So what is your kinetic energy? Kinetic energy is equal to half m1 v1 is r square theta dot square. Okay. Then Pe1. Pe1 equal to mgh. Here m1 because it's the only mass you can have m only. Okay. So mgh is this height. So which is r sine theta. Okay. So your kinetic energy, potential energy for the first link is done. And for the second link, Ke2 equal to half same mass and it is v1 square or here let's see v2 square. So here the displacement is r only. This length is r for the revolute joint and for the prismatic joint this length will include. So this r becomes r dot. Okay, so I can straight away put half m r dot square, half m r dot square, and then my potential energy is equivalent to P2 equal to, so mgh, so same thing, mg or sine theta. Okay. So now we have kinetic energy and potential energy for both the links. So let's derive Lagrangian Euler. So Lagrangian Euler equal to Ke1 plus Ke2 minus Pe1 minus Pe2. Okay. So Ke1 is half m r square theta dot square plus this one is half m r dot square minus m g or sine theta because the link is same. So only one thing, but I have given this PE2. So there is, or this PE2 is 0. So there's no, only one link. So it is mgr sine theta. Okay. So let's do tau 1. Tau 1 is dou L by dou theta. Okay. So let's derive dou L by dou theta theta dot. Okay. So in this, do you have theta dot? Yes. So differentiate this. So this 2 comes over, 2 to cancel. So m r square theta dot. So here you don't have theta dot. Here also you don't have theta dot. Okay. Then let's do the second term. D by dt of dou L by dou theta dot. Okay. Equal to. So here there are two variables. So one is r, another one is theta dot. So m, first we have to keep r square separate, so m r square theta dot. In the next case, you have to keep this separate, then this r square, it will be 2 r and then r dot. Okay, so this is your first term, and second term is dou L by dou theta. So here in the L, here no theta, here also no theta, but you have theta over here, so it is minus mg r cos theta. So this is done. Then next one is you have to calculate dou L by dou R dot here. R dot is the variable. Okay. So you don't have R dot here. Here you have R dot. So the 2 will come over here. So 2 get cancelled. You will have M R dot. Okay. Then here there is no R dot. So next one is d by dt of dou L by dou R dot. Okay. So which is M R double dot. Next one is dou L by dou R. Okay. So here you have R. So this 2, if you come, if it comes, 2 can cancel. So M R. So it is M R theta dot square. Okay. And then R dot because it is with respect to time. So M R theta dot square, then R dot. Okay. And then next one is, so this is done. Here you have, one second, let me put R. Okay, R. So we have done this. Here we not have R, but here you have R. Okay. So that will be minus mg. R is 1. So mg sine theta. Okay. So we have done all. Now we have to mix it. Then we have to combine it. Okay. So what is tau 1? Okay. So tau 1 is first term. What is the first term here? Yeah, this one. So it is m r square theta double dot plus 2m r theta dot r dot. Okay. So this is your first term, dou L, then minus dou L by theta. So minus minus will become plus mgr theta. Okay. Then tau 2 is, so here d by dt is one m r double dot, then minus the other term. The other term minus me, so it is minus m r theta dot square r dot minus minus will be plus mg sin theta. Okay. So you have a gravitation term, you have Coriolis term, and you have centrifugal term, and this is the acceleration. So let's combine. So here tau 1 and tau 2 is equivalent to, the first term is m r square. M r square is 0, then 0 m, then here theta double dot or double dot. Okay, this is done. Plus 2mr, then r dot theta dot. Okay, then you have minus mr theta dot square. Okay, this is one term plus m r c theta m s theta. This is with the gravitation. So your torque is composed of acceleration. Then this one is r dot and theta dot is Coriolis effect, and this theta dot square is centrifugal effect. and then this is gravitation. So it's this is the combination of these three effects. So this is the dynamics of RP manipulator. Then we'll see the dynamics for simple system, MBK system. MBK system means it is mass spring damper. So the next one is mass spring damper system. So this is the basic mathematical modeling for any mechanical system. If you take a car, you have mass of the car, and then when the car, I mean the spring action you have, okay, and then damping means the friction between the car tire and the road, okay, and also you can take arm, single arm robotic arm, okay, in this link has mass, okay, and then this if this link is attached to another link means here you have friction, so that is damping, so here you have friction, and then this hand stiffness is there, so that is called as spring action, okay. So we can simulate a simple arm as a mass spring damper system, because you have mass, and if it is rotated with the another body, then it has friction that is given by damper. And another one is spring action, which is stiffness of the arm. Okay, so let's take a simple mass spring damper system. So this is the mass. Okay, so here you have a spring, and then this is your dashboard. So here you're applying force. Okay, here you're applying force. As a result, you will have a displacement. And then this is, so this is K, this is B. Okay, so let's do the mathematical modeling using Lagrangian Euler. For Lagrangian Euler, we need, this is a single order system. So we have only kinetic energy. Kinetic energy is equal to half mass is there, V square. So already you have X. Okay, then V term is X dot. So it is x dot square. Okay, this is done. And then potential energy is equivalent to, so potential energy means the energy is stored in the spring. Okay, in the spring, the force is, I mean, the energy is kx. And when it is pulled, in starting position is x naught. And then when it is pulled, the spring is expanded up to xf, the final distance. So x naught xf k into x dx. So you can take k outside, and then if you take the integration, it becomes x square by 2 x naught and xf. So here we can take k by 2, and then you have to apply the limits x naught square minus xf square. Okay, so k by 2 x naught square is 0, and then xf is maximum distance only. So x square xf, or then if you take the square, it will be x square, so it is minus x square. So your potential energy is minus kx square, okay, or I can say kx square by 2, okay. So let's do the Lagrangian. So Lagrangian is equivalent to kinetic energy minus potential energy. Okay, so let's do that. So your kinetic energy, Lagrangian is kinetic energy. So what is your kinetic energy? Half m x dot square, and then minus potential energy is kx square by 2. Okay, then torque equal to, so d by dt of, so d by dt of dou L by dou x dot minus dou L by dou x. So let's take dou d by dt of dou L by dou x dot is 2 comes to 2 will be cancelled. So it is m x dot. Okay, and then minus dou L by dou x. So here you don't have x, but here you have x. So if you bring this 2 to get cancelled, so it will be kx only. Okay, kx, then we have to differentiate this. So this will be mx double dot, and then so this one is plus x. Okay, actually, in the previous case, what we have done is k by 2, 0 minus x the x square. Okay, so it is minus k x square by 2. When you bring this over here, it becomes plus. Okay, so this is the plus, and here, yeah, and then so one second, kinetic energy minus potential energy. Potential energy is minus, so minus of minus is plus, so it is plus kx square by 2. But here dou L by dou x you have, so minus kx. Okay, and one second, so here there's okay, so tau is mx double dot, and then it becomes minus minus plus kx. Okay, this is my L, and then this L is kx. Okay, so this is the linear system. You should not say this as a torque, this is a force. So force equal to mx double dot plus kx. So if you want mx double dot, so you can put minus f minus kx equal to mx double dot. Okay. So here this is your L. I think one second. Okay. So here yes. So here I think here I made one small mistake. Sorry about this. So let's take the formula k by 2 upper limit by lower limit. Okay, I put lower limit by upper limit. So this is the formula. So it becomes kx squared by 2. Okay. So here it is minus only. Then so this minus and then this minus will be plus. Okay. So here okay, sorry about this because here upper limit minus lower limit. I put lower limit minus upper limit, that's why the confusion is. Okay, so here plus, so mx double dot plus x. So this is the formula. This is the formula for a MBK system. So using Lagrangian Euler, we have derived this equations of motion for a MBK system using Lagrangian Euler system. Okay, so let's derive Lagrangian Euler formulation for single joint. Okay, so single joint. So let's take this is the one for single joint. Okay, so this length is L. This is my end effector. Then this point is x and y. Then angle it makes is theta. Okay, so let's do that. So the formula is tau equal to d by dt of dou L by dou theta dot minus dou L by dou theta. Okay. So we assume here is the point mass. Okay. You are assuming that your mass is concentrated at this point. If your mass is spread everywhere, then we have to consider the moment of inertia. But we assume that your mass is concentrated over here. Okay. So by practice, now we know that your V square is equivalent to L square theta dot square. Okay, because x1 dot square plus y1 dot square that you know. So what is your kinetic energy? Half m L square theta dot square. This is that. And then what is your potential energy? M G L is theta, sin theta. So now we have kinetic energy and potential energy. So L is equal to kinetic energy is half m L square theta dot square minus MGL sin theta. Okay. So let's do dou L by dou theta dot. So you have theta dot here. So 2, if you bring 2, 2 will get cancelled. So ML square theta dot. Okay. And then d by dt of dou L by dou theta dot is equivalent to ML square theta double dot. So this is done. Now we have to do dou L by dou theta. Here you don't have theta, but you have theta over here equal to minus MGL cos theta. That's all here. And we have to do this tau. Okay, so we have done everything. So now we have to do tau. Okay, so what is the tau formula? Tau equal to, we have given already, so just that the substitution. So it is mi square theta double dot and then minus minus is plus mgl cos theta. Okay. So you have acceleration, you have gravitation. Okay. And you don't have this Coriolis force because it is only one link. So since you have only one link, you will not have this Coriolis effect because for Coriolis effect we need two rotating body. Okay. So this is the equations of motion for the single link or single joint. So this is using Lagrangian Euler, and then the equation we derived is equations of motion. Here there is no Coriolis effect because your link one alone rotating, it is not rotating with the second link. Okay, so this is the basic equations of motion. So now let us discuss about forward dynamics and inverse dynamics. Okay, so here in kinematics also we have forward kinematics and inverse kinematics. So here let's see inverse dynamics. So it is inverse dynamics. So first let's see what is inverse dynamics. So you all know that the formula for tau is so m of q, it is the inertia matrix. So you have inertia, okay. Then you have one is Coriolis effect. So Coriolis effect means you have q dot and then q dot. So that you have q dot square and q dot. Okay, so for that. So here you have I mean both Coriolis effect and the centrifugal effect, and another one is G of Q. So generally your M of Q, I mean your torque consists of this is my inertia matrix. Inertia matrix. Then this one is acceleration. This one is velocity. Then you have Coriolis effect. So you have Coriolis and centrifugal. So in RR manipulator also we have, and in RP manipulator also we have. Okay, so in the RPA manipulator, let's recall what is that. So in RP manipulator, tau is equivalent to m r square 0 and then 0 m. Okay, so here these two variables are theta double dot and r double dot. Okay, plus we have 2m r theta dot, and you have one more r 2mr r dot theta dot, then mr theta dot square. This we have, and then mr c theta, then mr, sorry, m sin theta. Okay, so this is the general matter. So let's compare. So this is my gravitation. See, you have G. So this will give you the gravitation effect. Then this will give you two effect. One is Coriolis. So R dot and theta dot. Okay, Coriolis effect. Theta dot square will give you centrifugal effect. And then this is the acceleration. Since this is the RP manipulator, the variables are theta and R. So acceleration, this is M of Q. So this is your inertial matrix. Okay. So if you know the velocity, if you know the velocity or acceleration, then you will be able to find out the torque. So this is called as inverse kinematics. So what is inverse kinematics? Given what is given? Given the of vector of what is given? Manipulator position, manipulator position, velocity, and acceleration. If this is given, if acceleration and this velocity and position are given, then you will be able to find, or to find what? Torque. So this is called as inverse dynamics. So what it does, it maps, what is given? Motion. Motion means velocity, position. Motion to whom? Torques. So this is the concept of inverse kinematics. So in inverse kinematics, the given are manipulator position, velocity, and the acceleration. With that, we'll be able to find out the torque. So that is called as inverse dynamics. It maps motion to the torque. Okay. Then just opposite is forward kinematics. So let's see that. So next one is forward dynamics. So let's write the equation again. So what is the equation? Torque equal to m of q double dot plus c of q dot plus g of q. Okay. So in this, what is so this is the normal thing. So in inverse dynamics, we know position velocity. With that, we'll be able to find out the torque. But forward dynamics means, so you will know the torque, but we don't know the velocity, position, and acceleration. Okay. So we have to derive the formula. So how will we derive the formula? We have to keep this q double dot one side. Okay. So if you keep this term and then tau minus c of q dot minus g of q. Okay. And then you have to take the inverse. That's all. So this is your acceleration. Okay. So if I want to get the velocity means I have to integrate q double dot with respect to t. If I want to know the position, I have to integrate q dot with respect to t. So what is given in this given, yes, in this what is given talks. So given the joint talks or given, okay, let me draw. So what is given? Given a vector of joint talks. Okay, with this we have to find position, velocity, and acceleration. Okay, so I can say it maps forward dynamics maps torque because this is given to whom, to motion. So tau to q dot and q double dot. Whereas we'll see the summary here. So what is forward dynamics? So tau is mapped to q dot and q double dot, and then inverse dynamics is your q dot q double dot are mapped to tau. So this is your forward dynamics and inverse dynamics. So with this, the dynamics part over. So what is dynamics? Dynamics means it gives the relationship between, suppose if this is the manipulator means if you give force, then how the force is moving inward towards the base. And then here you have theta dot, theta double dot. So that is moving, propagating like this. So here force is given. And then you have to find out the relation between this applied force or moment, and then as the result, you will have some joint motion, joint velocity. With this, you should be able to find out the torque. You should be able to find out the torque. So here in each joint, you have motor, gear, and sensor. So you have to give the torque to the motor, then accordingly. Okay. So to find out the torque, we need motion. We need motion, velocity, and acceleration. So for that, we have to learn dynamics. So dynamics means it's a mathematical model which gives a relationship between the torque and the motion. Okay. So the dynamics can be resolved or the dynamics can be given by two models. One is Lagrangian Euler model, another one is Newton Euler model. In this course, we have seen only Lagrangian Euler model, which is energy based. And the Newton Euler model is force based. So using Lagrangian Euler model, we have derived the equations of motion for RR manipulator, RP manipulator, then single R manipulator, and then one simple MBK system, mass spring damper system. For all this, torque consists of one Q dot it has, and then Coriolis effect. It has Coriolis effect and centrifugal effect, then gravitation force. This is the combination, but one problem is it will not give the external disturbance, or it will not speak about friction. Okay, but anyway, that will affect the torque, then that will be taken care of by manipulator control system. Okay, so that's all for today. Thanks for watching.